Bellman-Ford algorithm last time. Okay, but we haven't had a chance to talk about the correctness. Okay, so but before the lecture, okay, a few things to talk about. Okay, first, this lecture is the second to the last, right? Okay, we have one lecture today, and next week we have one more lecture. Okay, and because we are in the middle of the shortest path, okay, shortest path has like 3 lectures. So we are trying to finish these 3 lectures in 2 weeks. And it doesn't look like, because we are in the middle of the second lecture, okay? So I'm hoping to finish like the shortest path, okay, today, okay? So it will only leave like 1 week, okay? It will only leave 1 lecture, okay, 3 hours. So there are 2 different topics I would like to cover, but obviously I don't think I can cover both. One is the min-max flow, okay? The other one is the NP-complete, okay? I think, okay, theoretically speaking, NP-complete should be more important than the min-max flow, okay? So my decision would be, let's finish the shortest path today, and the next week, okay, the last lecture we are going to focus on NP-complete, okay. So we probably have to skip the min-max flow. If you are interested in that part, I'm sorry, I mean, I ran out of time, okay? And I don't want to rush the lecture to cover like more material in like a short time, okay? So that's my decision, okay? And I'm sorry about that, okay? But if you look at the calendar, you will see that we actually cover a lot more material than what we did last year, okay? So I'm quite satisfied, okay? So that's the first thing, okay? The second thing is about the exam, okay? As we talked about the exam last week? I forgot, it was last week, right? You guys voted, okay, to hold the programming exam and the final exam in the same week, the 17th week, okay? It will be the week after the next, right? So the programming exam will be held like on Tuesday, and the written exam is going to be on Wednesday, okay, of the 17th week. And one thing, okay, I would like to apologize is that, okay, originally, because we now have like 93 students in the class, although it doesn't look like so, right? I mean, I think like we only like have like about like 1/3 student like attending the class, okay? But in reality, we have 93 students, and the lab computer, after, even though, I mean, both lab computer together would be around like 100, but after I check with the SNMG, okay, there are only about like 77 computers to be available, the other computers are either like out of function or like has some problem. Okay, so 77 student, 93 students, and we have 77 computers. So it looks like around 20 students will have to use their laptop. Okay, so so I discussed with the TA about this issue. Okay, one possibility is that we provide a sign-up sheet. Okay, so that like we will open 20 students to use their laptop. Okay, for the programming exam. However, the students who use their laptop for exam will have to record their screen, and provide that at the end of the exam. Okay, but you still have the benefit of using your laptop conveniently. After all, that's your laptop. It should be much more convenient for you to write program on your laptop, right? Okay, 因为这个很重要，所以我要用中文重复一次哦，就是说我。理论上下礼拜在考那个程式考试的时候，我本来跟大家讲的是说，因为我们现在有93个学生嘛，那我们那2间电脑教室加起来应该有100台电脑左右。可是我跟 SNG 去问了以后，他们说，他们的电脑事实上可以用，就是来考试的大概只有77台，就2间加起来。那我们有93个学生啊，那怎么办？那就看起来就是大概有快20个学生，我们必须要用，就是我跟 TA 讨论过，就是我们会开放20个学生用自己的电脑来考程式作业，程式考试。OK， 那这一部分当然因为不是那个就是我们那个电脑教室的电脑，那你用自己的电脑考试，那你自己电脑灌了什么东西，我们也不知道。我们能做的事是什么？我们可以做的就是说 ，OK， 我们会希望说，你来用你的 laptop 来考试的时候的那个同学，可以把你的那个萤幕录制下来。OK， 那萤幕录制下来，那你们不可能作弊嘛，因为你们作弊所有的行为通通都被 capture 起来。那考完了以后，那个连同这个萤幕的那个录的那个档案一起交上来，那这样子来确认说大家是公平的 ，OK？ 那当然你还是可以用自己的电脑来考，毕竟写程式用自己的电脑来写，比用电脑教室里面的电脑还是来得方便嘛，对不对？那所以 OK， 那就讲到这个 sign up sheet。OK， 我让这20个就说我们开放这20个同学在另外一间教室用自己的电脑来考这件事情。那个 sign up sheet 在今天12点钟会 upload 到EE-Class 上面。OK， 谁先去 sign up 的，那就谁先有这个权利，应该很公平嘛。OK， 就是。The sign-up sheet for you to use your laptop to take the programming exam, will be available, on EE-Class starting 12 o'clock, at noon today, whoever sign up first, the first 20 students who sign up, have this right to use your laptop for the exam. Okay. with a condition you have to record your screen, OK， 就是你必须要把那个荧幕录制下来，这样子，这才公平嘛，因为跟别的同学比起来，这样子，对，好不好？那这一次第二个要跟大家讲的，那第三个 ，OK，the third thing OK，which is also related to programming exam is that like some student ask about like I mean it has been like a lot of like programming syntax. I mean I have trouble and remember everything, you know. Is it possible to bring a reference book, okay, to the exam? Okay. Okay, to answer that, okay, I also discussed with the TA, okay. The decision is like this, okay. We will not allow the student to use the reference book because like it's impossible to check the reference book like from every student. However, we will provide like cheat sheet, okay, for the syntax of 3 different programming language. 因为我们允许你们用 C、C++ 跟 Python 来写程式的作业，跟那个当然也允许这3种程式的那种怎么讲，就是说用这种3种程式来来考这个考试嘛。那我们虽然不让你们带这个 reference book， 你们有些同学觉得说，哎，我记不了这么多的 syntax， 可能到时候 syntax 有错，那到时候就是说我的问题不是在说我不能够写出来演算法，而是说我 syntax 忘了。那这也是有道理，因为毕竟我们这堂课是演算法，我们不是程式设计课。如果程式设计课的话，那我就可能就觉得说你们 syntax 应该要记得，但是演算法毕竟不是程式设计课，那但是我们又不能提供让你们说自己带你的那个 reference book， 所以我们会提供那个，我不知道你们知道有那种像这种一张的，就是那种有一张里面就包含所有的 syntax 的那种，就是那我们会提供3张啦，因为有3个程式，那个有可能你们可以有3种不一样程式 ，C、C++ 跟 Python。那这个3张cheat sheet我们都会提供，我们会在class 上把这3个cheat sheet先提供给大家，让大家熟悉一下，这样子你们就是到时候我们在考试的当时，我们也会提供这3张，那你们可以先看一下，先熟悉一下那3张cheat sheet，然后考试的时候，希望就对你们有所帮助。这样子应该很公平吧？对你们应该就是说，你们担心那个 syntax 的问题的同学，应该可以适度的，就是减缓你们对那个我要背这些所有的东西背不下来这种担心哦。OK， 那这样子讲OK，any question？ OK， 所以 3 announcement. One is about like the material that we cover. Okay, obviously, I mean we don't have enough time to cover the min-max flow. Okay, the second one, the sign-up sheet for you to use your own laptop. Okay, that sign-up sheet will be available 12 o'clock today. Okay, at noon. Okay, if you want to do that, please check that out. Okay, the third one, the cheat sheet for the syntax of 3 different programming language. Okay? 好，回来 let's come back to the Bellman-Ford algorithm. So we talked about the Bellman-Ford algorithm last time, and we used an example to run through the Bellman-Ford algorithm. Okay, and at that time we ran out of time, okay, and we wouldn't able to cover the correctness and some additional discussion of the Bellman-Ford algorithm. So today we are going to talk about this stuff, okay. So first is the correctness, okay. So if we are given a graph, okay, it contains no negative weight cycles, then after the Bellman-Ford algorithm executes, okay, the dv means like the value saved in the array in the Bellman-Ford algorithm. It's going to be the total weight of the shortest path from S to V, okay, for all the vertex, okay. So actually the key idea here is that, okay, I mean, if you consider any vertex and consider shortest path P from S to V, okay, so this is a shortest path, okay, with the minimum number of edges, okay. And first we know like this path has to be at most n-1 long, right? I mean in terms of number of hops, where n represent the number of vertices, right? We talked about this last time when we talked about the Bellman-Ford algorithm, right? So this shortest path, as I said, must be shorter than n-1, okay? And we know if P is the shortest path, then we have from S to Vi, okay, here it's a V0, V1, V2, V3, to V, it's a VK, I believe. It's a VK. So basically, okay, so from S to Vi is going to be the shortest path from S to Vi is going to be the shortest path from S to Vi minus 1 plus the weight, okay, from Vi minus 1 to Vi. So in other words, we know like this is like the suboptimal structure, right? So in other words, any partial path, okay, is optimal path from S to Vi minus 1, okay, to Vi and so on, okay? So we know that, okay. So initially dv0 equal to 0, okay. This must be the shortest path. I mean, this is a starting node. Okay, dv0 is 0, okay. I mean, that's what we initialize for the first node, right? This must be its shortest path from S to V0 because we have no negative cycle, right? We have no negative cycle. So this one must be the shortest path, I mean, from S to V0 or from S to S, okay? So this dv0 is unchanged, okay, by the subsequent relaxation because it's impossible, okay, to be shorter than 0, okay. If it is going to be shorter than 0, okay, then obviously you have a negative cycle, okay. So, and also from previous lemma, we know like dv must be greater or equal to the shortest path weight, okay. So after the one pass through E, we obviously will obtain like the shortest path from S to V1, right? Because you have tried every possible edge. You have tried every possible edge to extend for one edge, right? So if there's if there must be one node, okay, that is like one hop away from the starting node, and it is the shortest path, right? Because otherwise, we wouldn't, this path, as I say, like the partial path must be the optimal, right? So this part must be optimal, right? So from V0 to V1, this must be optimal. And we have tried all the edges from V0 to actually to all the other to all the neighbors. So the V1, okay, the shortest path from V0 to V1, okay, after the first cycle, it's going to be there. And you know, this can be, you know, this is to be honest, this is not a very formal way to write this proof. If you want to write this proof formally, this should be an induction. Okay, so you can, you know, do this induction one step at a time. And from the first step, okay, this is, if we talk about induction, you'll get an idea. Oh, this must be, you know, the basis for the induction, right? And then from Vi minus 1, you can, you know, after once like a loop, you can advance for one more hop, okay, to Vi, okay, and then, you know, just like this, okay, from the first pass, okay, you get like a, you know, the shortest path from S to V1, or from V0 to V1. Second pass, you get like a, you know, shortest path from S to V2, and so on, okay. And after K pass, okay, dVk will be, I mean, it's going to be the shortest, the weight of shortest path from S to Vk. Okay, and I already told you, okay, G contains no negative weight cycles, so P is simple. Okay, there's no like a cycle contained in P. So the longest simple path must be smaller or equal to the n minus 1, which is like a number of vertices minus 1 edges. So we have this many loops. Okay, so Bellman-Ford algorithm guarantee that we must be able to find like shortest path. You can actually use this example check, okay, because our starting node is this one, right? You can see after the first pass, okay, we must be able to find, because like from A, well, sorry, here. Okay, from A to, it has two neighbors, B and C. So after the first pass, you can see at least one of them, the shortest path is known. Okay, you must be able to do that. So in this case, like after the end of the, well, so yeah, the first pass. I'm sorry, end of first pass. You can see that this one is the shortest one. Okay, and the end of the second pass, okay, from A to B to C, okay, that's the end of the second pass. Okay, so because C, okay, the shortest path from A to C is 2 hops, and so on. So you can verify this from this example, okay. So this also tells us that if a value dV fails to converge after n minus 1 passes, okay, what do we mean by fail to converge? It means that, okay, after n minus 1 like a loops, okay, if you run the loop one more time, and the dV value gets changed, I mean, when I say change, it must go down, right? Okay, when dV value becomes smaller for one more, if you run the loop one more time, then, okay, there exists a negative weight cycle in G that is reachable from S. Okay, otherwise, as I say, like the simple path, okay, the longest simple path is n minus 1. Okay, the only possibility that, you run the loop like, more than n minus 1 time and the dV value gets reduced is that there is a negative weight cycle that is reachable from the starting node S. So that is also why you can see that in our algorithm, we have a very simple part here. This part, basically, we are doing exactly the same thing in this loop. It's just like we are trying to run the loop one more time. Okay? And if there's any change, okay, then we report the negative weight cycle exists. And then terminate, because like when you have a negative weight cycle, the shortest path is not defined. Okay? So, yeah, that's about it for the Bellman-Ford algorithm. So, the next topic is that, okay, what can we do with the Bellman-Ford algorithm? Is there any particular application of the Bellman-Ford algorithm? Okay. One possible application of the Bellman-Ford algorithm is a special case of the linear programming. Okay, but of course, to understand what the special case of linear programming is, you have to first understand what is the general case of linear programming. Okay, so let A be a n by n matrix. This is n by n matrix. Okay, B be a n vector. So we have n number of unknown. Okay, we have n number of unknown variables. Okay, and then C be a n vector. This is C. Okay, in other words, we have n unknown and we have n number of linear inequation. Okay, because it's a small or equal to, okay, inequation. 就说我们有一个，这个是那个嘛，n 元一次方程组嘛 ，n 元，因为我们有 n 个未知数，对不对？就是如果用中文来讲 ，n 元一次方程组，那我们有 n 条方程式哦。This is just a matrix representation of what I just said. Okay, 就是把它写成矩阵形式的时候，那就这样长得像这样子。Okay, so under the assumption of this condition, given this condition, this inequality condition, okay. We want to maximize, okay, a particular, again, linear combination of your unknown variables. Okay, of course, like a linear combination of unknown variable can be written as a inner product. Okay, so this is like the general form of linear programming. Okay. Actually, this type of stuff has been there, okay, for ages. Okay. This is one of the most fundamental optimization problems, okay, especially in many like engineering field actually, but this has been studied in like operating system, okay，这中文就叫那个线性规划。如果你们是在if you have some classmates in like 中央没有工业工程哦，中央没有工，我们有公管，对 ，we have 公管所 ，we don't have like 工业工程 department, okay? So, but anyway, just want you to know, okay? In many industrial engineering department, okay, the 线性规划 linear programming is a complete 3 credit hour class. Okay, they spend a lot of time to study this thing. Okay, and not, of course, it's not like they study how to solve this for such a long time. Okay, I mean you do need to understand how to solve this, but on the other hand, okay, it is how you apply this on different scenarios. In 这有很多的应用哦。那在那边他可能会教你说，哎，你这个在什么样子的环境下、什么样的情境下面有很多的应用。事实上，这种线性规划哦 ，OK，this linear programming technique has been also used in many master students thesis。一直到现在，很多硕士生，如果你的那个硕士论文哦做的题目是可以把它变成一个线性规划哦，那你也可以用这个当做你毕业硕士论文的这个技术哦，就是说解题的技术，这是绝对没有问题的哦。所以这个是一个蛮重要的一个 branch，a very important branch in mathematics, especially like you know like nowadays like a lot of people use like linear functions to approximate like high order functions。在那个深度学习里面，事实上大家都是用线性方程组去逼近这个高维度的这个方程式哦，所以这种东西就变得越来越重要。But anyway, just want you to understand what linear programming is. But of course, as I said, we are going to deal with a special case of this, not a general case. So for general linear programming, okay, the most famous algorithm to deal with is called simplex. Okay, simplex algorithm. Okay, 我大学毕业的时候，因为那个没学好，去了清华工业工程读了1学期哦，就是那个因为反正那时候大家都在准备研究所，所以我也去，我觉得好像我也应该准备一下啊，我准备就看看，哎，好像这个系我可以考，我就考进去啊，但是那时候考进去单纯就是因为大家都在考，我就去考啊，考进去发觉我没有兴趣，所以我在那边读了1个学期啊，读了1个学期。我都在打谱哦，在宿舍打谱，那个下围棋嘛，但是 that's not important. The important thing is, okay, at that time when I took the linear programming class, okay, 因为那是清大工业工程研究所，那 at that time we learned the simplex method, okay, but yeah. It is a very practical algorithm, but in the worst case, it's going to become exponential. Okay, so it's kind of like a quicksort. We know quicksort, right? I mean, from this class, I mean, we discussed like a quicksort. I mean, many like several times. So you know, like quicksort it performs well in general cases, but in some special cases, for example, like if you are given like numbers in a certain order, for example, in ascending order, descending order, the quicksort is going to be perform very poor. Same thing for simplex method. In the worst case, if worst case, input presents, it's going to take exponential time to complete the algorithm. So it is like one issue. And I still remember back to like when I was at the Tsinghua University, it was about that time. Okay, somebody, a mathematician, invented an algorithm. Okay, it's called interior point method. That was like I believe at that time when 那个是什么？那个是大概1991、92 about 1991, 1992. I believe like you guys wasn't born at that time yet. Okay, most of you okay wasn't born at that time. 那时候就是这个方法才刚被发明哦。This method is great because it runs in polynomial time. It has been proved. Okay, it's great because as I said, like linear programming has so many applications. So if you are able to improve the algorithm that solve linear programming, that's a big contribution. Okay, so this mathematician, okay, the interior point method that he invented, okay, it is great. It can compete with simplex method, but still now, simplex method has still been used very extensively. Okay, you can see that simplex method is so popular. Okay, is so popular. Okay, but these algorithms are more complicated. Obviously, we are not talking about the general problem anyway. Okay, and so another particular case is that, okay, we call such a problem feasibility problem. So in this problem, okay, we do not have optimization criteria. We just try to see if there's a possible solution for such a set of inequalities. Okay, 就是说这个 feasibility problem 就是这个 linear programming 的特别的例子哦，它其实它没有这个，它没有右边这个，你不是说给定这个条件来去最大化这个，不是没有这个，那你就是这个，你就只有这个，它就是看说在这样子的n 元一次方程组里面有没有解？有没有解 ？OK， 大家知道嘛？就是你如果说有一些这个不等式哦，你把它组合起来，可能是没解的，对不对？所以它就是要看有没有这种情形哦。那所以说呢，这个叫做 this is called feasibility problem. But in general, okay, if you do not confine anything, then the feasibility problem is as hard as the ordinary linear programming. Okay? But again, let me repeat it. We are not dealing with general case. Okay? Our case is like this. We are doing feasibility problem. Okay? But our problem has a very special form. Okay? We want to solve a system of difference constraints. Okay, difference. Okay, so or put it another way, in our linear programming, each row in the array in the matrix A, each row in matrix A contains exactly one 1 and one negative 1, and all the rest of the elements will be 0. Okay, or if you try to rationalize that by the inequality, basically we are just all the inequality will look like x1 minus x2 small equal to 3, or x2 minus x3 small equal to negative 2. Something like this. So you are given like many such inequalities with only two variables. And 1 has the coefficient 1. 1 has coefficient -1. Okay? And so this is, as I say, a special case of feasibility problem. Okay, so all the this inequality has the form like this: xj minus xi smaller or equal to wij. Okay. So, how do we solve it? One possible solution in this particular case is to assign x1 to be 3, x2 to be 0, x3 to be 2. You can try to plug in this set of values in here. Okay, 3 minus 0 is 3. Okay, so that's, this one is satisfied. And 0 minus 2, okay, is -2. So that this one is satisfied too. So 3 minus 2 is 1. 1 is smaller or equal to 2. So this whole, all these three inequality is satisfied. Okay, but how do we find such a solution? Okay, and put it not, I mean, to make it worse, what does this to have anything to do with shortest path? Right? Interesting, right? You can convert each inequality into something like this, making each vertex, each unknown variable as a vertex. Okay, xi to be vi, xj to be vj. If you have a inequality xj minus xi smaller or equal to wij, then you just have h from vi pointing to vj with wij to be the weight of this h. Okay? Then, obviously, the A matrix is going to have a dimension, okay, number of edges times number of vertices, right? Because you are going to have, you know, this many vertices, okay, as your column, right? Column. Okay, and the number of rows is going to be depend on like number of inequalities. Okay, and number of inequality, because each inequality is going to be translated into an age. So this one, that's why we have this here, right? So if you try to do that, okay, then this problem is going to give you a graph, right? This problem is going to give you a graph. Okay. So we say if the constraint graph, we call such after this translation, we call this one a constraint graph. Okay. If a constraint graph contains a negative weight cycle, then the system of differences is unsatisfiable. Why? If there's a cycle, it's unsatisfiable. Because, let's say if there's a cycle, there's a negative weight cycle, V1 to V2, blah, blah, to Vk to V1. Then we have this one, this actually indicate, because if we have this one point to this one, it means we have x2 minus xy smaller or equal to W12. This W12 is the the weight of this edge, right? And so on. We have all this. And then if you sum up everything on the left-hand side, everything cancel out each other, so it's 0. On the right-hand side, it's going to be the weight of the cycle, which is what we know. Okay, it's a negative weight, right? It's negative weight. It's not a 0. So you end up have a 0 is smaller or equal to something that is smaller than 0. That's impossible, right? So therefore, no value for xi, okay, regardless how you assign the value of xi, you just cannot find a possible assignment to satisfy all these constraints, obviously. Right? So that's the first thing you need to know. Okay, so now we are gradually like converting, gradually like bringing this constraint graph, okay, to the shortest path discussion, because shortest path discussion has, obviously we discussed negative wave cycle in the shortest path, algorithm. Okay, so then we need to further discuss this. Okay, but before that, I think it's about time to take a break. So let's take a 10 minutes break. When we come back, we will continue to discuss this application. Okay.